Okay, everybody, how's it going? I hope either holiday or Halloween or whatever you might be celebrating, you're doing well. Any questions administratively about what's going on in the class? It seems like we've kind of hit a repetitive process, right? You know there's an assignment due, you know we have the notes, you know we have the videos, you know that I'll probably get some helpful videos out the night before the assignment's due. So that's kind of the pattern. And hopefully you also are keeping track, if you have not already done so, when you have the lab, so you can get over there. Okay. The next exam is on November 17th, and unless there are significant issues, I think what we'll probably end up doing is keeping people in the rooms that they were assigned, because I think we had a good balance. We might change it up a little bit, but we'll probably change the seating assignments. Okay. Okay, hold on. Let's hope that everything's back online. That was a little scary. Yep. All right. Okay. Technical questions? Yes.
When you say that there's a assignment due, you mean the
Right. Just in general, I'm just saying. At this point, right? You know, there's maybe a little bit of confusion in terms of how the class operates at the beginning, but I think people now we kind of know what's happening. There has been something kind of interesting that's occurred. I think there's a little confusion about when office hours might be. Okay, so I have my office hours after class on Tuesdays and Fridays, and Praj has office hours on Tuesdays and Thursdays. Okay, the office hours are in the syllabus. Some people occasionally pop on Zoom at other times, and I understand that with Canvas and the way we have the Zoom thing set up, that maybe it looks like there are office hours every day. No, okay, they're not. It's as given in the syllabus, all right? So there's been maybe a little bit of confusion on that. And if you have questions, come to office hours, okay? Or send them through Canvas, all right? There was, I guess, a little bit of a question about number 4 on last night's assignment. Hopefully the video clarified that a little bit, but this was on the combined loading, or the combined cylinders, right? So what you had essentially is 2 cylinders, right, that were concentric. And so there was question, I have a gauge pressure P, all right? And that gauge pressure is with respect to what? Well, it's respect to like outside, okay? The whole system, that's the gauge pressure we're talking about. So a lot of times we've talked about, gauge pressure being the relative difference. The easiest way to think about relative difference and not confusing yourself is just say, here's 0 absolute, right? And then I just have P absolute on the inside, okay? And that will be the same as gauge pressure. Then the other question comes down to, okay, what is the, is it an action reaction? What, is it equilibrium? What are we talking about between the pressure between the 2 cylinders? Well, just for that, right, what we were saying is that if this is the outer, okay, I don't know what's going on, why it doesn't stick. All right, and this is the inner. I'm not quite sure what's going on. I accidentally left my the pen that I normally use, and luckily this pen seems to work. It was in the office, so I didn't have to. I was always tempted to send a message to the classes, anyone have another pen I could use? Because we did that once before. But I found this one. Anyway, so here, right, you still have, let's say, this P absolute on the inside, okay? And this is 0 absolute on the outside, okay? And there's going to be some pressure, right, acting on the outer cylinder. And since, today we're going to add stresses directly to each other, okay? But when we're doing equilibrium, often it's nicer to think in terms of forces or moments instead of stresses. But here, what I said, as I explained it, right, you could say, okay, that's the like P contact, if you will, P sub C, right? That pressure is acting over an area, and it's an interface, so that area is going to be the same on both of the outer and the inner where they meet up, and so that you're going to have that same pressure also acting on the outside of the inner. Okay? And so that's more of a third law, okay, with an equal and opposite reaction than a second law, right, which is when we sum the forces and make them equal to 0. I like the comments that were in the GroupMe about this. I think you had pretty much gotten there. And I actually didn't see the comments in the GroupMe until after I finished the video. I was like, oh, okay, well, good. I'm glad that we're online, because I think your comments started at 9:30 p.m. and I think I posted that video around 10:45 or so p.m. Okay. Any questions on this aspect? It's a tricky problem. These problems I don't necessarily expect, especially the first time, for you to get the first time, to get without a little bit of help. And yes, even there, right, there was the resource to David Roylance's page on pressure vessels. Okay, and some of you were able to get that. Yes, question. Shalami, right?
Yeah.
Yes.
So why didn't you the absolute pressure on the inner cylinder subtract the PC from that instead?
Good question. Okay, so that's where it comes down to a definition of context, right? Or I could see you thinking, the gauge pressure is really, the P minus the PC, right? That's the question. Well, if you had a gauge, right, it's going to be hard to measure that interface pressure, okay? But I could see how that's confusing. Yeah, I could see how that's confusing. And that's why I'm trying to say, no, the way we're defining the gauge pressure, it's between the inner of this system and the outside of the outer cylinder. Okay, good points. All right. Any other questions? All right. I like that word, all right. And I like ums. We have maybe one of the hardest conceptual lessons today, or sessions, that we're going to cover. And again, it's okay if this material looks a little bit new. It's okay if we don't get it right immediately. We can discuss it in further detail. And I think as I post some of the videos for the examples, some of the concepts will be simpler. It's a key session, though, because what we're going to do today is combine the different types of loadings that we've been looking at, use superposition. We're going to be looking at normal loads. We're going to be looking at shear loads. We're going to be looking at normal and shear loads. And so this session doesn't necessarily tell you, will it break or not? That will come later. All it's trying to do is essentially figure out what the tensor looks like at a given location. What do I mean? The stress tensor is what I'm talking about, right? So today we're saying, you know what? I know that a bar that's uniaxially loaded has 1 sigma 1 sigma x, 1 sigma, whatever it is, right? But it's uniaxial loaded, has 1 stress, 1 normal stress, 1, 1, 1, 1, uniaxial, 1 axial stress, right? What we're saying is now when we put multiple loads on that bar, or we put multiple loads on a structure, it's not just sigma x. And you already knew this. You already knew beams are going to have transverse shear stress potentially and some bending moments, right? Or bending stresses, right? So you already kind of knew this. Today is kind of the time where we formalize it. So our goal is to essentially populate the stress tensor. I don't really think I say that explicitly in the slides, but that's maybe one way to say it. So it's let's check them off. Do I have sigma x, sigma y, sigma z? Do I have tau xy, tau yz, tau xz, right? There's 6, essentially you have 6 options. And most of them are going to be 0, okay? Because we're still kind of working in 2.5D. The goal, though, is to figure out how those individual configurations with loading and geometry end up resulting in the particular stresses that we care about. Okay? And so these are some drawings of the types of systems that we're going to be analyzing. And you're like, hey, these don't really look that different than what we've been doing. And they aren't. Okay, you've pretty much, I mean, maybe this one right here. Let's see. Maybe this one, like that's not working. Come on. Why is that not working? I think I know why it's not working. Hold on. Okay. Maybe this one right here looks a little bit different, but these others are pretty straightforward in that we've dealt with them. This one is a little bit different because it comes off at a right angle. Okay? But I won't say that you should have seen that before because I'm not allowed to say that anymore. Okay? But that's a configuration we'll go into. Okay. So the different types of loading. What are the different types of loading? When I say different types of loading, what are the different structures and the types of stresses we've been able to calculate? Just, what do you think? Tell me something. What have we learned how to characterize in terms of stresses and strains at this point? Yes, Mark.
Normal loading.
Okay, normal loading in particular?
Axial.
Yeah, axial. Okay, great. Okay, what other types of loading have we looked at? So the bar, right? Yes. Okay, so transfer on what? On beams, right? And what kinds of stresses are we talking about there? I mean, what are your options for the stresses on a beam? I'm not saying you have to give me formulas. I'm just saying what types.
Shear.
Okay, shear is one, yeah. Okay, what else? So transverse, what does transverse mean? Let's go back to that. What does transverse mean? Come on.
On the wide side of the view.
Just open up the dictionary for a second. Let's back out. What does transverse mean?
Perpendicular.
Huh? Yeah, or across. Okay, that's all it means, right? So when we talk about transverse loading, well, we got to talk about across what? Okay, and so we're talking about on a beam, right? And we have different types of loads that we apply. Okay, so then we have a beam. What kinds of stresses can we characterize? Well, there's transverse shear stress we talked about, and what else? Yes. Yeah, there's this bending, right? So those are the kind of the two options you have when it comes to beam bending. But there's actually one other that we haven't. We'll talk about today. We'll gloss over it, but it's that they can also be normally loaded, right? So you can have a beam and you can have an axial load along the beam as well. Okay. What else? What other systems have we characterized? Yes.
Torsion.
Yeah, so torsion. And what's the stress involved with that? What type? You have two types essentially. So you have a torsionally loaded system. When you have twisting, are we talking, I mean, what are the, so, I mean, when I talk about sigma x, sigma y, sigma z, those are normal stresses. So you have, the answer here is either normal stress or shear stress. Okay, so tau xy, tau yz, tau xz. That's it. We have normal stresses and we have shear stresses. Or we have both. So back to this question. If it's torsionally loaded rod, what type of stress are we dealing with? Exactly, okay? This is not going to make it. This has too much wind resistance. All right, so maybe Brennan, if you can pass it over. Oh, no. All right, that was way off. I thought I was doing better. I haven't figured out those, but I hope he can make it over to you. All right. And then what else? What else? Oh, you have good aim. You should be doing this. All right, what else? Yes. Okay, so distributed, yeah, that's a distributed load, right, is going to be for a wide variety of systems, right? That could be on torsion, on a rod, okay? That could be on a beam. It can even be on a bar, right? We saw how gravity affects our integral of p dx over EA, right? So that's kind of a type of external loading, shall we say? Okay, that's fine. What? Yes, Michael.
Axial loading.
Huh?
Axial.
Okay, we already said axial loading. Okay, that's okay. Give me another one though. Twisting. We already said twisting. Okay, pressure. Yes, like a pressure vessel. Yes, that's kind of the other one that we could be dealing with. All right. So, so pressure in a vessel, a thin wall pressure vessel, and then what types of stresses does that induce? Not compressive usually, huh? So here, we'll let. What are you going to say over here? I'm sorry, huh? No, not shear, not shear, not shear. We're talking a thin walled pressure vessel. What you all were working on last night, huh? Yeah, hoop, there it is, which is what? It's an axial or a normal stress. Who said hoop, there it is? Where, hoop? Oh, there's no way. Come on. I'm going to hurt. By the end of the class, I will be able to throw up there, I think. But right now, I cannot. Yeah. Oh, actually, I could. Okay. That underhanded. I have been teaching the wrong way, I see. All right. Okay, so anyway. Wow, that's really embarrassing. Okay, anyway, so so hoop stress and a longitudinal axial stress, okay? There's one other, so yesterday I almost brought in some tree clippers, okay? Because I was super excited that, oh wow, these are excellent examples of shear, right? So I was thinking about, how we talked about single shear, for example, right? And I think in the future maybe you can write in the suggestions like you should talk about simple and double shear before you talk about torsional shear, right? Because that gives a nice example of shear stress, okay? But yeah, that's kind of just forced over an area, and you get an average shear stress. Okay, so those are the different configurations that we've discussed. All right, let's see if I forgot any, or I don't line up with my slides here. Okay, yep, I think that's I think this was about it. Okay, so we've actually done quite a bit if you think about it. Right, you came into the class. And we didn't even talk about stresses in another class, okay? And so now we have this toolkit that says I can calculate, at least for these kind of simple configurations, which are present in a lot of the devices and a lot of the structures we see in the world. I can calculate these different types of stresses, okay? So what we're going to do today is say, hey, what happens when you have multiple loads or configuration that can induce these different types of stresses simultaneously. Okay, that's all we're trying to do. And then we got to keep track. It's really an accounting problem. Okay, we got to keep track of the different types of loads. Okay, if we go back to the first class actually, and we said also that if we had a bar, and if we also talked about beams, and we talked about rods, right? We kind of figured out, hey, what's the maximum supportable load? We didn't go into any of the physics or the calculations of stress, right? We just said, this is the rule for now, we'll explain why. And at this point also, you have an idea, and we'll cover this in much more depth, but at least for a single uniaxial loading, okay, or kind of one type of stress, we have an idea that, if I can think about, especially for the normal stresses, if I've characterized the material and I know what the yield strength of that material is, and the yield strength is a normal stress, then I can say whether or not the system's going to fail. Okay? So we also know how to essentially, look at the amount of force that a structure will have and relate that force to the amount of stress that's going to be in that system. In that, we now know that if I have, for a uniaxially loaded system, sigma equals F over A, it has to be less than the yield strength. That's for one direction. Okay. Now, torsional loading, again, we said that the supportable load scales, right, with diameter to the third or area to the 3/2. And now, okay, we know that the shear stress is going to be TC and J, TC over J, right? And that has to be less than some type of shear stress limit, okay, or the shear yield, the shear yield strength, okay. And again, that's just for one type of loading, right? That is when you're twisting that rod. And if we if we're considering the max, right, and we know it's cylindrical, right, and then we can calculate the J, that's pi over 2 c to the 4th. We can get another equation there. That's also got to be less than the shear strength. For transverse loading of a beam, we said this in the very beginning. All right, we had that the supportable load scales with h squared, it scales with b, and it scales with 1 over L. Okay, we now know that sigma is equal to negative my over I. Okay, and that has to be less than the yield strength in order for us not to have any yielding and for not to have failure. And we can break that down a little bit further, and we can say, okay, this is what the sigma max would be for the system where we have a force being applied on the end. Notice I didn't say anything about the transverse shear strength here, or the transverse shear stress, because as we described in the assignment, I guess two classes ago, that typically is much less. The shear strength, the shear stress is typically much less than the bending stress. Okay, it has to be a very narrow or very short beam for us to be thinking that shear stress. I can't get my words straight. Shear stress is going to dominate the failure. So just coming into this, we can see that the supportable load does in fact scale with h squared. We see it in the denominator here for the sigma max. The supportable load does in fact scale with b. We can see it here. And the supportable load does in fact scale with 1 over L. If we increase L, then the bending stress is going to increase and we get closer potentially or exceed the yield strength of the material. We've also spent some time on superposition. Now the superposition that we were talking about has referred mostly to combining forces to figure out what the combined displacement might be. Okay? Of course, you can also combine forces, especially if they're in the same direction at the same location, to figure out how you would add the stresses that you have together too. Today, maybe it'll be a little bit more clear on how we handle situations where we're adding another load somewhere else or in some other place that does in fact mess up, well, not mess up, but we use superposition to figure out what the new stress is, right? So here, let's just kind of, again, review and take a look at what Hibbeler instructs us in terms of superposition of forces and stresses. we're making some assumptions. One is that the material is homogeneous. Another is that the material has a linear elastic modulus, and we're also kind of making this assumption that the deformations are small. Okay, and so the kind of classic example of where beam bending fails is for large deformations. When we have, let me see if I can get this to work. If we have something like a beam and we're loading it with a force P on the end, right? We're saying that P is more or less going to be vertical the entire time we're doing this loading. But later you'll see when we do beam bending and stuff, we can calculate the deflection. And if you have something that ends up looking like this, right? Well, that's really bad. You have questions. Is P still going downward? Is it still vertical? Did it go with the end of the beam? Okay, these types of questions affect the answer you're going to get. They affect the linearity of the results that we get, and they also affect the assumptions and the mechanics that we use to derive either the deflection equations or the stress equations. So for large deformations, there are analytical responses, but again, that's where simulation might play a beautiful as a beautiful tool. Okay, we're sticking to the simple configurations. As you already know, these simple configurations are enough to keep us busy. Okay, the general procedure has been to use method of sections. Right now, method of sections is everywhere. It's in the pressure vessels. It's in the bars. It's in the rods. It's in the beams. It's in the trusses. Okay. Method of sections is critical to being able to understand what the internal loading looks like. It may still seem weird to have this internal force, or weirder or stranger or more difficult to understand the internal bending moment. Okay, the thing is just to back it out, even if it's conceptually a little bit difficult. Just take a breath and take a look and say, I need equilibrium to be satisfied. All right, I know what external equilibrium looks like. Just pretend you're doing external equilibrium, but with a slice. We have to determine the normal and shear force components, along with the bending and torsional moment components. Okay, forces should act through centroids, and moments should act about centroids. We'll talk about actually kind of a counterexample to this force acting through a centroid in a second. We got to determine individual normal and shear stresses for each type of loading. So we have normal force, shear force, bending moment, torsional moment, and thin-walled vessels. Okay, so it's like we've got this whole toolkit now, and we look at a problem and we're like, okay, I now know what type of system I'm dealing with, and I can go ahead and figure out the internal stresses. And now you've been waiting for this for a little while, but we can finally add the normal stresses to each other. Okay, so you're like, phew, finally. You're like telling me, because I've been saying, be very careful with equilibrium, right? Be very careful with equilibrium. So what we're saying is, if you're at a given location, you can add those normal stresses to each other if they're in the same direction, right? Would you add a sigma x and a sigma y together? Of course not, okay? Do those sigma x and sigma y have an effect on whether or not the material will yield? Absolutely. We haven't gotten to that step yet, right? But just if it's at the same location, in the same direction, and the same type of stress, we can add those to each other, right? You want to add a tau xy and a tau yz to each other. Okay? You might think about tau xy equal to tau yx. That is true, right? But when we do superposition, we got to make sure that these stresses are the same type and in the same direction and at the same location or on the same phase. So let's do a little bit of true and false. Okay? So question 1, or statement number 1. A bending moment and axial force might both contribute to a normal stress. Is this true or false? Anyone? Yes?
True.
It's true, okay? And I didn't say, you know, and how is that? Why don't you explain that, Mark?
Well, an axial force already, like in its nature, contributes to a normal stress, and then a bending moment creates a bending stress.
Yeah, that's right, okay? This is the penultimate, all right? All right, so I only got one more. All right, a torque, so this is true. Let's just mark that down as true. No, why do I have, I don't know, oh, now it works. I don't know, I just had to scribble maybe. Okay, so that's true. A torque and a shear force might both contribute to a shear stress. Yes? Yeah. Yeah. What? How so, Stephen?
We already know that shear force will produce a shear stress. So even if the torque doesn't produce any component.
Okay. Yeah. Yeah. Okay. Good. Okay, we describe the stresses within thin-walled pressure vessels as pairs of shear stresses. That's false. Who said that? Okay, yes, thank you. All right. We add bending stresses and shear stresses directly to create composite stresses. What's that? Also false, right? Okay. For a cantilever beam, the maximum supportable bending stress scales linearly with the base width of the beam. True, right? We just said that. Okay? And for a torsionally loaded cylindrical shaft, the maximum supportable shear stress scales with the radius cubed. We also just said this. Okay, so this is also true. Okay? Okay. So that is also one of your homework questions, all right? But these are some of the things that we've learned. And I think, you know, it's occasionally good to look back and say, hey, we have actually, you know, the class is ripping along. We're at session 16. And do you know how many sessions we have in this class? 25. All right, so we are actually over, we've crossed the halfway mark. Okay. It's exciting. Okay, so let's look at superposition of normal loads. Okay, so these might be somewhat, this might be the, I don't know, it could be simple, it could not be, we'll see. All right. The general procedure, okay, is that we section the material, we determine the normal and shear force components, along with the bending and torsional moment components. Okay, we determine individual normal shear stresses. All right, we just said this, and add the normal components to each other. Okay. All right. So our possible sources of normal stresses are bending moments, normal force, thin-walled pressure vessels. Okay. These are our options. Okay. And you know, this might be a little bit of a misnomer now that I think about it. Like this is these are normal loads. Let's just say that this is really superposition of normal stresses, though. Okay, because you could have a bending moment that's contributing, as we're seeing here. So if we go here, let's imagine that we have a beam with an applied bending moment, and we have also this axial load, as shown. The beam has a width or a base B and a height H. All right. So the question that's not really here, but the question really is, what are the normal stresses at locations A and B? Okay, so we want to know what are the normal stresses. Okay. So before we even do this problem, let's just use the think method. Has anyone ever watched The Music Man? It's like this musical from The Music Man. Anyone? Anyone? Come on. There must be some people. Music? No? 76 trombones? No? Okay. So, quick synopsis of this musical, or this movie, right? From a movie musical. Okay? A salesperson comes to town and doesn't know a thing about bands or band instruments, but he just wants to sell to all the people instruments, make the money, and leave town quickly. All right? But he, for a variety of reasons, he ends up having to kind of be there for a while, and he has to teach them how to use these instruments, even though he knows nothing about music. All right? And so what he says when they get together for their rehearsals is we're going to use the think method. Okay? So what we're going to try to do, not that I'm a charlatan, hopefully, okay? But we're going to try to use the think method here, all right? So let's just think, okay, where or how do these loads, the bending moment that's been applied, and the force, how do they affect what's happening at A and B? Okay? So, for example, at A, is FAP, what is it going to do? Is it going to put it in tension or compression? Assuming FAP is positive. Yes. Tension, right? And at A, is MAP going to put the A in compression or tension? Compression, right? Can you see that? Without doing any math, if I take this eraser, okay, and I'm pulling on it, I'm stretching it apart, and I'm applying a bending moment at the same time, you can kind of get this idea, oh, the pulling apart is going to cause A to want to spread out, right? It's going to be tensile loading. And this bending is going to cause the top to be under compression. Okay. B, on the bottom, all right, that's simpler now because, well, we've done the top, right? B is going to be under tension in both cases, right? You can see that. I'm pulling this thing apart, so it's going to want to be in tension. I'm causing this bending moment to cause this, the different material elements on top to get closer to each other, and the different material elements on the bottom to get farther apart from each other. Okay, so before that was not a good idea. Okay, before we even do any math, we kind of got an idea of what we're going to have to add and what we're going to have to subtract, okay, or what we're going to have to add appropriately, and this is superposition. So if we take a look at this cross section and we draw it like this, we can say, okay, there's the B, that's the base or the width, and if we're doing transverse shear stress, which we're not right now, but if we were doing transverse shear stress, that B would be a T, which would be thickness. Okay, but I typically, anyway, that's just how Hibbler calls it. All right, that's great. And H is the height, which I think of as thickness, but H is height. So in this situation, the external loads look something like the following, okay, where we have the MAP, the FAP, right, and we know that the FL is going to be equal to MAP, and that the FL is going to be equal to FAP, and the ML is going to be equal to MAP, right? This is just using external equilibrium. And if we want to talk about the internal bending moment, we take a slice, like we do here. Okay. And we also are a little more careful in this case. Let me see if I can be more careful too. Okay. We have our N. That's what I mean by careful. So usually we don't draw N, but now it's a good idea to make sure that we're accounting for any axial loading that might be present, like the FAP. And the M is equal to MAP, right? That's M here, that internal, right, is equal to M. Well, okay, so we have ML well, m minus ml is equal to 0, right? So that means that m has to be equal to ml, and ml is equal to ml. Right? And the internal shear force is going to be equal to 0. There's nothing in the vertical direction in this problem. Okay? And the internal normal force, we have n minus FL is equal to 0. So n has to be equal to FL, which is equal to FF. And so now let's start to think about the stresses. The stress from n, okay, remember it's usually a good idea to think about these stresses in terms of internal loads. Right? Of course, we can equate them to the external loads, but we're first trying to figure out what the internal loads are because the stresses are internal as well. Okay? So we get the stress from n, and that's going to be equal to what you could call sigma NA or sigma NB, all right? That is, you know, we're doing some averaging here. So yes, could there be some like edge effects and various things on the, you know, top or the bottom? Yeah, there could be, okay, but for our intents and purposes, as long as we're not in the air above the beam, but we're in the beam, we're going to say that those normal stresses are going to be the same. And what are they? Algebraically, what's the equation here? What would it be?
Force over area,
Yes, and that would be?
the axial stress.
Yes, and specifically for this problem?
The N
Yes, which is equal to
is equal to the FL or
FAP, right? And
the area based on height.
that's right, that's it, okay? So we have N is over A and then N over BH, and the N is equal to FF, right? Okay, so stress at A from the bending moment, okay? So this is going to be using the flexure formula, okay, which is that we have negative my over I. Okay, y in this case we're going to say is going to be h over 2, right? That's the distance to the outer surface from the neutral axis. And I is going to be equal to bh cubed over 12. And this is going to be under compression. So I often do not, that negative sign, it's important, that negative sign. There's that, you know, the negative my over I, that negative sign is an important thing. I often, though, don't keep very careful track of it. I just say, oh, it's got to be negative, and I put it, you know, I figure out the magnitude, and then I put the negative in front of it. Okay, but here we can be careful. All right, we can say that we have minus, right? The internal m is map, so we have minus m. Okay, the height h over 2, it is above, right? So it's not below. Below, it will be minus h over 2. Above, it's h over 2. Okay, you see that? So that's h over 2 there, and then we have the bh cubed over 12, so we get minus 6 map over bh squared. For the bending stress at B, okay, we have a very similar result, and at this point, you just be like, I know it's going to be just the opposite sign of this, but to kind of be a little bit more careful and to write down exactly what I just said, is that we have negative my over I. Y is now equal to minus h over 2. I is bh cubed over 12. So if we do negative, negative, we get a positive. And that's just going to be 6 mf over bh squared. Right. Any questions on this? Pretty straightforward, right? Yes, Michael.
For this, just be consistent, I guess, with negatives to avoid any.
Sure, yes, and use the think method, quite frankly, right? Before we even did this algebra, we looked at the problem and said, is it going to be in compression or tension, right? And if it's and so we knew that it was the bottom was going to be in tension because of the bending moment, and we knew that the top was going to be in compression because of the bending moment. Now, the actual final value, we don't know if it's going to be positive or negative because we have a positive F app in both cases, right? So that's causing tension. And, well, in the bottom case, we know it's going to be positive, right? Because they're both positive plus positive is equal to a positive. But we have a positive plus a negative, and depending on what those magnitudes are, then then the top could be negative or positive. Okay. So if we go on, what we can say is that the stress in the beam from N is just, it's just sigma N across the whole thing. The stress profile from M is going to be having this 0 at the neutral axis. It's going to be in compression at the top, and it's going to be in tension at the bottom. Okay, we kind of said all this, but this is now showing the the nice linear gradient that you get by varying y. And then now let's go ahead and we can select elements, orientations, A and B. Okay, and we can write out. Okay, so you see this is A. Okay, and x direction was this direction. Y direction would be this direction. Z would be, in this case, coming out of the board. Okay? And it's almost like we're overcomplicating this. All we want is that it's going to have a positive contribution from FAP over BH, and we're going to have a negative contribution, right, from the MAP, okay, which we described here. Sorry. Okay. And then at B, okay, we can say that we have the sigma B, and we're going to have them both adding to each other. Okay. I mean, I was kind of making fun of my own drawing here, okay, because it's kind of trivial. It's just uniaxial. I mean, it's like, yeah, it's in one axis, all right? But these drawings are going to become very important when we have more complicated structures. Okay, so we want to do this. Any questions? Is this clear? This is a pretty straightforward, I think. Okay. Well, okay, maybe I shouldn't say it. But so what questions? Any questions on this? All right. Well, let's keep going. Okay. So this is the second question on homework, and it is asking us to determine the normal stress, okay, along the x direction. So this is x coming out. It's axially going here. All right, and we have a force P not acting at the centroid, right? So this is off axis. And we're kind of making some, simplified approximations. This point A is on the outer surface. It's on this edge. It could be over here. It could be over here. We're not, we're making some approximations here, okay? We're not going to say, yeah, I mean, maybe it'd be better to put it like in the middle here, all right? I'll explain why that is in a second. But we're trying to figure out what the state of stress is at A. Okay. Before we even do this problem, if we use the think method, what's the state of stress? This normal stress. What kind of stress are we expecting out of this problem? Before we do any algebra, before we do any equilibrium, what type of stress do we expect to have there? Yes, Stephen?
Axial bending.
Okay, so you're expecting some axial bending. Okay, interesting. Yes, I agree. Yes. Why do you say axial bending?
It's on the edge, so since the force isn't in the center, it's going to cause it to bend slightly. Yeah. So sometimes people use the technical term you have an eccentric. I can't even use it. Eccentric loading here, right? So it means that it's not on the centroid; it's off axis, and so yes, that would be contributing a bending moment. Okay, that's good. What else can you tell me about the type of stress we're going to have?
At point A, because the way the stress is, will make it go like this.
Okay, hold on. At point A, what do you mean? I don't know if I understand what you're gesturing.
It's squishing it.
Okay, squishing it. I understand that.
So it's stretching A, I believe.
Is it stretching A? If it's, you said squish. When you said
Why not?
squish,
Wouldn't it go like this?
oh, you think it might be buckling outward or something?
Yeah.
Okay, so we're not talking about buckling here, all right? It's just basic using what we know. But you said squish. When you say squish, do you mean compression or do you mean tension?
It'd be compression.
Right. So the other thing is that, look, there's a force coming down, pushing down, and it kind of seems to make sense that that force is going to be compressing it. And then the way this is working with the eccentric, like the eccentric loading, okay, there's a moment being applied. That also seems like it would cause this side to bow out, right? And this side to kind of curve in. So from both of these scenarios, it looks like point A is going to be under compression. Okay, does that make sense? Okay. Why I should have put A on this midpoint instead of here, because you could also, and we're not going to consider it because we're going to say that B is much smaller than A. You could also say, oh, well, this is off-centered in this direction as well, right? In the Z direction as well, okay, X, Y. And it could be like adding an eccentric loading that's B over 2, okay, for the thickness, but we're going to ignore that.
Would that put A in tension?
Yes, yes, it would. That would put A in
I think
tension.
that's what it was.
That's what you're looking at? Okay, all right, that would put A in tension. Good. Okay, but I'm looking at the larger contributions, right? And you can see that B is much smaller than A. Okay, good, thanks. All right, so now let's do this out. We have a slice that we're going to take from the top. So this is the top surface where we have the P acting, and we have A at this location right here. And we're going to say that this P is acting some distance A away from the center. And now we have to draw the internal loads. So remember, internal loads, we do follow conventions. So how would you draw the internal loads here? How would you do it? Someone who hasn't really, Jonathan.
No, I actually have a question on that.
Oh, okay, fine. Go question, yes.
Shouldn't the P be in the center? Can we show that it's in the center of the P?
So look, this is P. I'm taking this perspective here. Let me see if I can do it.
Is this like looking at the side A?
Yeah, we're looking from this direction, okay? And so P is just on the right side. A is on the right side as well, okay? All right. Okay, so what types of internal loads would we draw here? Okay. Now you could argue a couple different ways of doing this, all right? But let's just say that I'm considering the top of the beam as what I would say is kind of the left, all right? And I would say that that bottom open slice is kind of the right. So if I just rotated it kind of like this, now which way would you draw the internal loads following convention? And how many internal loads are we talking about? This is method of slices. Yes?
There should be a shear stress going to the top.
Okay, so good. All right, so there should be a shear force. All right, yeah, we'll call it, because internal loads usually we before we get to stresses we talk about forces and moments. So I agree. Okay, I'm going to have this shear force. Okay, going to the left. All right, so good. That was good. And then I also have a normal load coming out. Right? And I have a bending moment as I've drawn there. Okay? If I said that was the right. You get the last one. Okay. All right, that was close. Plus or minus one person. Okay, so yes, Brennan.
Quick question. So you said that P is, if we were to consider the B to actually not be super small, like if it was actually like a normal size,
Then it would be different. If B were not super small, then you would want to consider it.
but like if it was normal, then you said it would put A in tension.
Yeah.
How
So
would it put A in tension?
okay. So let's like what we're saying here, right? If I have essentially what we're talking about here. Okay. So we got. Okay, like this. All right. Then, if I were, or maybe it's better if I put it on the opposite side. You know, if I put it, let me do this. If I put the P over here, okay, and I have my point of interest over here, right, then would we agree that because I'm applying a bending moment that's kind of like this, okay, that's going to put A in tension.
But if it was at the center of Washington.
So, yeah, so if A, yes, so if A were at the middle, okay, I should have probably put it here, so to avoid this whole controversy of what's happening in the B direction.
I'm sorry, but if he was up the middle, it would have put an A in tension.
Oh.
It's at the center, right?
Yes, that's true too. Okay, that's true. It would just be compression. Yes, that is true. Okay. So good. Thank you for the clarifying comment. Okay. So yeah, because if it were at the middle, yeah. So that's right. So I'll take that back. Yeah. So since P is at the middle. You could argue that that's not good, that the B direction doesn't matter. Yeah, because we have, because it's at the middle in that direction. Yeah, so, okay, so you're right. So as long as if we put it on one side over here, then we'd have issues, but since it's acting from the center, we're going to assume that it's making zero contribution. Good. All right, thank you. I like this, guys. I like this, peoples. All right, so now, let's keep... So, do we agree though with these, at least for our internal conventions? Okay. So we have N, we have M, and we have V. Okay. And can you see? Maybe I'm making this too big a deal, but can you see that this is? There's a little bug over here too. That's fun. Okay, you can see that this is. No different than here is the V, here's the M, and here is the N. Oh my goodness, I don't know what's going on here. Oh, I don't know what's going on. I'll be happy to I'll make sure I bring my normal pen back next time. Okay, so moving on. Once we have our internal forces outlined here, or internal loading, because M is not a force, obviously. We can write out that we have N plus P is equal to 0, so we have N equals minus P. And we can say that the normal stress is going to be equal to minus P over 2A B. Right? That's because we have A and A, so that's going to be 2A. And we have the summation of the moments at O, so we're going to specify that location, as equal to 0, and we have M minus AP equals 0. So M is going to be equal to AP. So in this case, the Y direction, okay, would be going from the middle to A. And that means that when we do the sigma M, we have negative my over I, and we can then write that minus APA over this quantity I gives us a bending stress of minus 3P over quantity 2AB. Yes?
Can you explain the 2A times P for the normal stress?
Sure. So because this is the entire height, right? I need to know. This is the problem with putting points at the edges, I guess, right? Because it's what we're assuming is that, at least from the axial normal loading, okay, that the stress is going to be the same across the whole cross section. So if I had just put P in the middle here, right, then I would just have P over the area, right? And what's the area? What's the cross-sectional area here? Exactly, that's all. All right? Yeah, so essentially what we're saying is 2a is equal to h as well when we do the bh cubed over 12. So we get that quantity for the stress due to the bending moment, and we have that the total is going to be the sigma n plus the sigma m, and we're going to get that it's just minus 2p over quantity A and B.
I don't.
What?
No, it's
Okay, we're good? All right. Any questions? So this is how you can calculate and add normal stresses to each other. When one is caused by axial loading with a force, and the other is caused by a bending moment. I see people writing things down. Questions? So now the next thing we're going to talk about is what happens with shear stresses and shear loads. So once again, general procedure. Okay, section the material, determine the normal and shear force components, or along with the bending components for moments, and then we're going to determine the individual normal and shear, and we're going to add the normal components to each other and add the shear components to each other, and then we're going to show how this looks at a particular location. What are the possible sources of shear stress? Well, you have the pure shear because of simple or single or double shear, and we also have the transverse shear stress. Okay, so those are kind of the kind of two of the ways that it can be looked at, and then third is thinking about the torsional, the twisting that can take place, and if this is going back to the transverse shear stress, okay, so that's out of order, all right. But transverse shear stress, we also know that you can figure out the maxes for transverse shear stress and bending, and it's going to be 3/2 times the average shear stress if it's a rectangular cross section, and it'll be 4/3 times the average shear stress if it's a circular cross section. Okay. So this is all, let's just clarify this a little bit. These, okay, all of this stuff is for transverse shear stress. And of course, this is for the torsion. Okay, so this was, I guess, yeah, let's do this. Okay, and this is kind of like single or double shear would be kind of this situation. Okay. Now, here we go. This begins the adventure. What do we see here? We see that we have a right-angled beam that is circular, and how many external forces are acting on this, excluding the constraints from the wall, or how many external loadings, excluding the constraining forces, or constraining force and constraining moment? Just one, right? It's P. And we have this location A. Hold on, I gotta move over here. We have this location. Okay. So if we use the think method, before we even mess with this problem. We're doing shear. What can you kind of say? Which direction do you think the shear might be acting? Which direction would the shear stresses be acting? And how are they being induced? Hold on, Michael. And someone else. Let's see someone else. Some ideas, some guesses. And I'll say here that there's also bending in this problem. Okay, there is bending. Okay, and but what are you all thinking? Yes.
I'm thinking because the wall is trying to resist. I assume it's attached to the wall statically, so I assume when someone's like taking like that's like looks like a crank, so when they're turning it, it's the wall trying to resist the turning. That's what the shear is.
Yeah, so you can definitely see like there's a twisting, right? There's a torsion element to this, right? Okay, and so that's going to be causing there to be that contribution, yeah.
It looks like the little a is going to be like this radius.
Okay. Yeah. Okay. So let's break this down. Okay. So we have a cross section. Okay, and you see, so this is X coming out of the wall, and now it's coming out of this face, and so you draw lots of little pictures like this, and we have a Y, all right, like this. Okay. And A is over here. Okay. We can also draw it again. Often it's great to have multiple drawings. Okay, so like in this case, now I've just drawn a neutral axis, and you can see when the transverse shear stress is the maximum on a neutral axis. So we'll say that we also have a transverse shear stress present here, okay, like this, and that can also, okay, be given as simply 4/3 tau average. Okay, the tau average is going to be p over pi c squared. Okay, and the tau v will therefore be 4p over 3 pi c squared. We have shear stress from torsion. Okay, and so that can be given as PA. All right, that's the amount of torque that's going to be causing this to twist. Okay. And that can be calculated as follows. And the torsional shear stress can be calculated as you see there. Okay. If we go and look at this, right, we have torsion causing a shear stress in that direction. Okay, you see that? These are the shear stresses as we cause twisting. Okay. So that can be given as we calculated 2pa over pi c to the cube. Okay, and the transverse shear stress, okay, that's from the beam bending problem. That can be given as tau v, okay, is equal to 4p over 3 pi c squared. Okay. Okay. And if we look at this element, right, so this is X coming out, and you see that these are shear stresses, okay, like this. So this one's coming up, then another one on the opposite side has to be going down, and this one is to the left, and this one's to the right. This is just so we have equilibrium. And then when we flip this, right, so now we have X, we take this X and we put on the right side, because normally when we draw these, we have X on the right and Y vertically, okay? We get the following, okay? Just like this. And that is a representation of the of the shear stresses that we have. Okay. Any questions on this? This is there must be questions. I went through that quickly. Okay, what is maybe unclear? Okay, go ahead.
For the bending part, not the torsion.
Okay.
The part where the bar goes out like this, is that all raising at like this?
Okay.
Or is there?
So what do you mean? So like if we go back, so what is your question?
So at that image, I know it's raising this way, but is at like the intersection is also raising this way?
So this, you're saying this force, is it going to cause this, let's say this point right here where the laser is. Are you saying is it going to cause it to move up?
Well, I have a feeling that, but also would it cause like that?
Yeah, so this is going to go up as well. It's causing a twist, right? So you can start to, yes, so we haven't talked about deflection here, right? But you know that the angle of twist, right, would be TL over JG. So you could figure out what the angle of twist is here. And assuming that this doesn't bend, but of course it probably would, but if it didn't bend, you could figure out how much vertical displacement you have just because this main region, or this region is twisting, right? And it would be TL over this JG for that matter. Is the angle times radius gives you displacement. Okay. Other questions? Yes?
What T equals to A?
Say that again?
What T equals to no A?
This one?
Yeah.
Tau? Okay. This is the torsion formula. TC over J.
Next to it, T equals to
This one?
on the right.
I think he means the T is PA.
T is equal to PA. Oh, the torque. Okay, right. Okay. This is a lever arm that has length A, right? So, if I have a cross section, if I have a cross section, or one way is to write that I have some torque like that, right? Another way to write it is to say that I have a lever arm and I am applying a force, right? Then that can induce that same torque. So this torque is the same in this case, I'm saying, as the force times the length. Does that make sense, right? Like, there are two ways to... Have you ever taken a bolt out of a... Okay, who's, changed a tire? Okay. Okay, great. So, when you change a tire, you have to remove the bolts, correct? Who's ever had trouble removing those bolts? Yeah, what happens? Why do they get stuck?
Strip, shear.
Yeah. Well, I mean, they can get stuck, because rust, corrosion, right? And then they get some binding, right? And if they're not well lubricated, anyway, or they were tightened really hard. If they're tightened really hard, whatever, they get really tough. So what's the trick to loosening these bolts? Huh? You extend, right? So you try to get as much of a lever arm as you can. Okay? So this is no different. We're talking about a torque that's being applied here to a shaft, and if I make a torque being applied, right, to this shaft, and in this case the shaft is this direction, right? I could apply, I could try to put a screwdriver, right? If I'm trying to take, it's impossible, right? Unless you have an air gun, right? Where then you're applying the torque directly on the bolt, right? So those guys, but even then, right, they've got to hold it because that thing's going to whip around, okay? Or you do it the manual way, which is you have a huge wrench arm, or a huge wrench that you can apply that torque. Okay, does that make sense? That's where that torque is coming from. Good question. Okay. my goodness, the time has flown. We're so far from being done. Okay, so, all right, let's, at least we'll cover this idea, and then I had to create some other videos to do the homeworks, all right? The basic method is still the same. These are the different types of loading and stresses that we're interested in, okay? Now, let's imagine that we have this torque being applied, and we have this location A, and we have a force being applied out this direction. If we're looking at this configuration and we're looking at, you see this is the X direction, this is the Y direction, this is the Y direction. We're just taking the square that the square that we've got at location A, and we've redrawn it, and we've redrawn the coordinate axes. Can everyone see that? Easy peasy lemon squeezy. All right, so now the tau xy, this is a little bit tricky, all right? But this is using kind of a combination of the think method and a little bit of our intuition. Do you see, why would I draw the shear stress up on the X face? Why would I do that? Yes, you're pointing. Please speak. Huh? Not because of the force. Because of the... No. The tau xy. Why is tau xy vertical there on the left side? Shear because of the moment, the T-ap, right? Can you see that this screwdriver-like torque is going to be wanting to lift this side more than this side? Can you see that? Like, the angle of twist is going to be positive about the X, right? So this is where using kind of the think method plus some, plus what we've been doing with deformation helps us draw appropriately the direction for the shear stress arrows. This is kind of important, and it's kind of confusing, all right? And I kind of only got 3 minutes. So we would take this element, because it's weird to have X coming out of the left side, and what we would often do, or what I suggest you do, is that you flip it so that X is coming out of the right side. And when you flip it, this is what it looks like. Okay, you see this? This is just flipped over. So now this is tau xy, right? And it's actually positive. The way we define shear stress is this is actually a positive representation. Because on the X face, in the X face in the Y direction, that shear stress is going up. Yes, Jonathan?
So why is it that the shear stresses at the top and the bottom are facing those ways if P is only pulling out towards the X direction?
Because it's got to be under equilibrium. The element has to be under equilibrium.
Then why is one of them at the top and at the bottom? Shouldn't they be able to connect the sides?
What are you talking about? These two or these?
No, I see on top and bottom of the square there's
Yeah, once you know one, you know the rest. Okay, because these always have to point against each other, because this one has to be the opposite from this one for equilibrium in that direction. And then these have to be in the opposite direction of these to prevent twisting. So once you know one, you know all four. All right? All right. The normal stress is simple. All right, that's not too bad. So you can now say that sigma is equal to P over pi c squared, and tau xy is equal to this. Okay? These cannot be added to each other. One is a normal stress, one is a shear stress. Ba-ding, ba-doom, ba-doom, you're done. Okay? We can't do anything else here. Okay? There's another example, and I'll try to go through this in video, and then I'll try to go through the problem that you have as well for the homework. Okay, but we actually are pretty close to being done on this. Okay, so let me go ahead and just get the attendance up for everybody. Just give me a second, and I'll try to answer questions that might have come up. This material, I think, this is probably conceptually, or how do you say it, Visually, it's probably the most difficult that we're going to do.
So my professor is going to get this due to work the entire time, and so I basically have to.
Okay, and once again, okay, here we go. I don't know why it does this. I just, every time it does this now. You gotta be kidding. Oh no! Okay. I'm not gonna mess with it. Just do this. All right, just take that. All right, because I don't wanna mess.
Yeah, but it's like really not.
Okay. Thank you, everybody. I hope you have a very good weekend. I have office hours now, in case you want to talk about anything.